The next thing we need to discuss is pressure, temperature, and something called STP, or standard temperature and pressure. So pressure can be defined basically as the force, try it again, force of all the gas collisions or gas particle collisions with a surface. Funky W, sorry about that, with a surface. That's a U, that's an R. You guys know how to spell surface, I just can't write it with my pen. So pressure is the force of all the gas collisions that are bombarding and colliding with some sort of surface. If you add those all up, that is what we call pressure. Now, the way that we first discovered that air pressure changes is with something called a mercury barometer. So what you see here is basically you have a little container of mercury at the bottom. As you guys know, mercury is a liquid at room temperature. And someone took a graduated beaker or a test tube, and the graduated means it has those little markings, right? Kind of like a graduated cylinder. So they took a cylinder and they stuck it into the mercury. And what they noticed as time went by is that the height of that mercury kept going up and kept going down, not like quickly, but over days, weeks, and months. There was some variability within the height of that mercury at the top of that cylinder. What they then discovered is that there is something called atmospheric pressure. Again, we don't feel it because we've been born under this pressure, but basically remember, air is a real gas, not an ideal gas. So there is gravity pushing on the air particles, the gas, nitrogen, oxygen, carbon dioxide, so on. All those gas particles are getting squished down by gravity. So down here at the surface of the Earth, the air pressure is much greater than as you go higher and higher and higher in altitude. If you've flown in a plane, you know how that feels when your ears pop. That's a change in the air pressure. If you go too high, and you can't even breathe if you lose pressure in the airplane. If you were to lose pressure, you're going to pass out because there's not going to be enough air because, again, most of the air and the oxygen is pushed down to the surface of the Earth by gravity. So, again, as that air is being pushed down by gravity and the weight of it, it's going to push that mercury up the cylinder up into the inside. And so, what they determined is that air pressure exists and that air pressure changes. So, if you watch the news, the weather portion of the news, sometimes they talk about air pressure and high pressure front and low pressure fronts. Those are often associated with weather. That's what they're talking about, is that some weather fronts can bring in a real low pressure, which means that the air coming in that front just doesn't have as much pressure as what's in front of it. Okay. So what I really want to point out is not only how it was discovered and what a mercury barometer is, but also I want to point out this particular unit right here. So what we used was millimeters of mercury. So that relates right here, mmHg. mmHg literally means millimeters of mercury. Now, millimeters is a distance, right? But what we're talking about is the distance of the mercury up inside the tube, which again is directly related to the pressure of the air pushing the mercury up inside the tube. So that's where millimeters of mercury comes from. This one right here stands for atmospheres. So at sea level, we are under 1 atmosphere. It's just a standard. Like we just said, okay, sea level, anywhere you're on the globe, that is 1 atmosphere. Okay. That is equal to 760, again, 760 millimeters of mercury, 760 mmHg, which is also equal to 101.3 kilopascals. kPa stands for kilo pascals. Then those are all the metric pressure units. So these are what we use in the metric system. The ones in the parentheses on the right are either empirical or they are metric, but they don't really follow into the SI units. So we kind of don't use them as much, but you have all heard of PSI, that stands for pounds per square inch. Torr is another one. And if you've ever been scuba diving, bar is another one. So all 6 of those are equal. There is no difference whatsoever between the pressure of 1 atm and 760 torr or 14.7 psi. I want to pause real quick because I want you guys to think about what air pressure really is, right? Think about that for every square inch, right? Pounds per square inch, for every square inch in 3 dimensions, there's 14, almost 15 pounds pushing on that square inch of air. If you guys have ever picked up 15 pounds, it's pretty heavy. Think of that being squished onto 1 square inch of air. That's the pressure that we live under. But again, I don't feel pressure right now because I was born pretty much at this altitude for the most part, right? And therefore, I've lived here roughly at this altitude my whole life. So again, it's normal to us. Much like, say, if, well, I can't think of another example, but anyway, I just wanted you guys to think about how much air pressure that really is, because 14, almost 15 pounds squishing on a little square inch of air is actually quite a bit if you think about it, right? Okay, now that we understand what pressure is, the 6 different units of pressure, again, the first 3 are really the ones we're going to use more or most frequently. What we need to do now is actually learn how to convert from one pressure into another pressure. Now, this is going to look really familiar because this is basically going to be another conversion. Think unit 6 and unit 7. Luckily, it's only one step, don't worry. So if I need to convert 112 ATM, which by the way would obviously crush us and kill us, just as a side note, what I would do is I would take 112 atmospheres. Okay, I'm going to put atmospheres down here. You guys having deja vu? What I'm going to do is I'm going to put kilopascals above it. And then I'm going to use the numbers up above to do my conversion factors. So for the bottom, I have ATM, that's 1. At the top, I have kPa, kilopascals, that is 101.3. So again, if I go ahead and put that into my trusty sidekick, I call my calculator, 112 times 101.3 divided by 1. That gives me a pressure of 11,345.6 kilopascals. That's how much pressure that is, which is 112 atmospheres. All right, let's go ahead and try another one. So if I was going to take 899 torr, and I needed to convert that into atmospheres, I would take torr, put it on the bottom to cancel it out, and I would put atmospheres up above. So again, torr's on the bottom, there's torr, 760. Atmospheres is right there, that's 1. So I keep doing that, I'm sorry guys. So what I'm going to do is I'm going to take my calculator, 899 times 1 divided by 760, and I'm going to get 1.183 atmospheres. Okay, let's go ahead and do one more. I think you guys are kind of getting the hang of this. If I had, this is a massive amount of pressure, 5,678 kilopascals, and I'm going to convert that into atmospheres, kPa, atmospheres. Again, let me change my colors. My kilopascals is right here, it's 101.3. My atmospheres is right there, that's going to be 1. All right, so then I'm going to go ahead and type that in. 5,678 times 1 divided by 101.3. Again, there's a decimal right there. Oops, I did not mean to do that. 0.3. And that comes out to be 56.051 atmospheres, or 56 times greater than what you and I are experiencing here on at near sea level. We're about 600 feet above sea level right now here in Richardson, roughly. Okay, so that's how you do a pressure conversion. It's super simple. I do want to point out that those pressure units at the top of your screen right now are given to you on the formula chart. The reference material that says conversions, constants, and sig figs, on the back of that are all the constants, and they give you most of those pressure units. So you don't need to memorize those. You just need to be able to find them. You need to be able to use them to convert from one to the next, okay? So that's not too difficult. Again, pretty similar to our previous 2 units. Moving on, temperature. Temperature, again, is a measure, actually, it's really a measure of the kinetic energy of the particles. I should have put that in the notes, but it is a measure of the kinetic energy of the particles in the substance. So, for example, again, if the molecules are moving ridiculously fast, then that's going to be what we call hot. If I was going to touch that gas, or that gas was going to touch me, I would probably be in uncomfortable or possibly scalded. If the gas molecules are moving super slow, then I would probably feel that at my skin as something quite cold. So our skin has the ability to detect the speed of the molecules hitting it, which is what we basically call temperature. So temperature, as you guys know, we have Fahrenheit and Celsius. Fahrenheit is the empirical and Celsius is the metric. Well, in science, we use a third one, and it's called Kelvin. Now, Kelvin is just capital K. There is no degree symbol. It's just capital K. So it's a number K, not number degrees Celsius. There's no degree symbol, okay? It's just kind of weird. It's just K. So what we have here is something called absolute zero. You may have heard of this. Absolute zero is the temperature at which all molecular vibration stops. Okay, all molecular vibration stops. There is no movement. They have completely still. That is the coldest theoretical temperature possible in the universe. We as humans with our labs have been able to get very close to absolute zero. I don't believe we've ever been able to get exactly to it, but we've been able to get very, very close. If you guys watch science fiction movies, sometimes they talk about cryogenic freezing and how we can keep tissues or a body or a brain indefinitely and then without it aging. That is typically being held at absolute zero, at least again in science fiction. The reason why that would work is because that object, that body, that tissue, that organ would not age at all. There would be no molecular vibrations, therefore there's no molecular activity, therefore there could be no aging. So if we could take a person or whatever, freeze them at absolute zero, then in theory, we should be able to thaw them at some point. This is the hard part. And then they would be the same age. Now, the thawing is the hard part because that's where it gets a little bit messy. But anyway, that's science fiction. So absolute zero is, well, 0 Kelvin. What that is equal to negative 273 degrees Celsius. Now, think about that for a second. Celsius goes from 0 to 100, right? 0 is freezing water. 100 is boiling water. I love the Celsius scale. It's so brilliant, right? So simple for us humans. Freezing to boiling. That is a span of 100 degrees Celsius. Now imagine going from 0, which is freezing water, and then go down another 100 equal to freezing to boiling, and then another 100 equal to freezing and boiling, and then 73 more, almost 300 times, or excuse me, 3 times colder than freezing water. Not 3 times, but well, would it be 300? Math escapes me. Nevertheless, it's almost 3 times colder than the range from boiling to freezing water. If you can kind of wrap your head around that, it kind of gives you an idea of just how cold we're talking about. Negative 273. There's nowhere on the planet that ever gets close to that cold, ever. Okay, this is again the coldest theoretical temperature possible. All right, all that being said, guys, what you guys need to know is how to convert from Kelvin to Celsius and vice versa. This is super easy. Basically, whenever you have a Kelvin, or excuse me, you have a Celsius, you add 273. Sorry, that sounds wrong. Yeah, that looks wrong. Basically, your Celsius is always going to be 273 greater than your Celsius. I'm sorry, guys. I am totally blanking out right now. Sorry about that, guys. I had a little pause there, a little brain lapse. So yes, that is correct. I'm sorry, guys. So basically you take your Celsius degrees Celsius, and then you add 273 to it to get Kelvin. It's always 273 because remember, absolute zero is negative 273. So Celsius will always be 273 greater than Kelvin. That's the way it's always going to be. Dang it, I said it wrong again. Kelvin's always going to be higher than Celsius. Why am I getting so confused on such a simple concept? Wow. Anyway, so let's go ahead and try to convert these really quick. So basically what we have here, guys, is, So if we have 25 degrees Celsius, then basically what we're going to do is we're going to add 273 to it, because remember Kelvin, as I just forgot for some odd reason, is going to be 273 degrees, or excuse me, higher. So this would be 298 Kelvin. Again, not degrees Kelvin, just Kelvin. So if I had negative 40 Celsius, I would add 273 and I would get 233 Kelvin. All right, if I was going to have 200 Kelvin, I would need to subtract 273 and I would get a very chilly negative 73 Celsius, okay? So again, the Kelvin's always going to be higher. I feel so dumb right now. Kelvin's always going to be higher, so you either add up to Kelvin or you subtract down to Celsius. So if I have 0 degrees Celsius, of course, that is 273 Kelvin, not absolute zero. Again, absolute zero is 0 Kelvin, negative 273, don't get that confused. If I had 0 Kelvin, again, here it is, this is absolute zero, 273 degrees Celsius. If I have 120, I'm going to add 273, and I'm going to get 393 Kelvin. So it's super, super simple. And again, on the formula chart with the constants and the equations, they give you this too. They tell you that Kelvin is 273 above Celsius. They give you that number. Again, you don't need to memorize the number, just like the pressure units. You just need to know how to find it, and as always, how to use it. Finally, the last thing we need to talk about in this video is something called STP, or standard temperature and pressure. Standard temperature and pressure, notice there is no standard volume. It's standard temperature, standard pressure. What we have here is basically it's freezing. We don't use Celsius, right? So it's going to be 273 Kelvin. That is our standard temperature. And then it could be any of these 3 pressures. These are our standard pressures. Again, remember, they are all equal. There is absolutely no difference between one atmosphere, 101.3 kilopascals, and 760 millimeters of mercury. They are the same thing. They're interchangeable. Those are the standard pressure, which again is sea level, and that is at 0 degrees. So freezing at sea level, that is standard temperature and standard pressure. Okay, we're going to use STP and standard temperature and pressure much more in the rest of this unit. So make sure you guys look for STP, or standard temperature and pressure, in the questions coming up in the next videos. And as always, guys, thank you for watching, and sorry again about my lapse in memory.